Hello everyone, my name is Zara Khan and my roll number is 225062. My topic for the presentation is theory of field extensions. So let us start. First thing is to understand what is a field. So field, any algebraic structure f, comma plus, comma dot is called a field if it is a commutative ring with unity having multiple inverse of every non-zero element if of it. So for example, we can take that 0 plus comma dot this, or real number which is r comma plus comma dot, this is also example of a field. Then subfield. So any non-empty set of S of a field F, if F is a field, so any non-empty set S of field F is called a subfield of F if S comma plus comma dot is also a field. For example, set of real numbers R is a field subfield of C comma plus comma dot. So set of real numbers is a subfield of this field. Then theorem. Let's come to the theorem. The necessary and sufficient condition for a non-empty subset S of a field F to be its subfield R. So now we have two necessary conditions given. For all A comma B belongs to S, it will imply that A minus B also belong to S. So if A and B are belonging to S, then it will imply that the difference between these, the A minus B, will also belong to S. Then another necessary condition will be that for all A comma B belonging to S, it will imply that A B inverse also belong to S. Now the proof of these two necessary conditions is given below. So now let us prove the necessary conditions. So proof. Necessary condition: if S is subfield of F, if S is a subfield of F, then S comma plus comma dot is also a field. So it is a subgroup of F under addition and multiplication. Hence 1 and 2 are proven. Now we will look to the sufficient conditions. So if A belongs to S, it implies A minus A also belong to S. A minus A is O. So O also belongs to S. Now additive identity exists in S. Again, if O belongs to S and A belongs to S, then it will imply that A minus A belongs to A minus A, which is minus A, it will also belong to S, like given in the sufficient condition. So it is just the reverse. Then additive inverse of element S exists. So also for A belong to S and B belong to S, if A and B both belongs to S, S is closed under addition. S will be closed under addition. Hence associative and commutative as obvious. So if it is closed under addition, it is obvious that it will be associative. It will be associative as well as commutative. Then as so S comma plus is an abelian group. So S comma plus will be abelian group. Now for the second one, A belongs to S, which means that A belongs to S, it will imply A inverse belongs to, which is equal to 1, which will belong to S. Hence unit element exists in S. Multiplicative inverse of every non-zero element exists in S. Again, if A belongs to S and B belongs to S, then A belongs to S and B inverse also belongs to S. So A multiplied by B inverse, an inverse of that will also be equal to AB, which belongs to S. So S is closed under multiplication. Addition we had proved it is closed under addition, and it is proved closed under multiplication also. Now next is that S comma dot is also abelian group, because S plus 1 is abelian group, it is associative, it is satisfying the property, and now S comma dot is also abelian group, it is closed. Now distribution laws will hold in S if it is in F. So S comma plus comma dot is a field. S is a subfield of F. Now characteristic field. Characteristics of a field. For any field F, the least positive integer n for which ne equals to 0, where e is multiplicative identity of field, is called characteristic of a field. Next we will have a theorem for this. So the characteristic of a field is either 0 or a prime integer. Now to prove this theorem, we have a proof given where n is characteristic of a field and f will be equal to, characteristic of a field f, then ne will be equal to 0, where e is the unit element of f. If order of e is infinite, then ne is equal to 0, which will imply that n is 0. So characteristic becomes 0. Because e is 0, order of e we assume it to be infinite, then ne will be, n multiplied by e will be 0. So n is 0, which is that the characteristic is 0. But if order of e is finite, then n is not equal to 0. Now to show that n must be prime, let, if possible, n is equal to n. n1 is not equal to 1 and n2 is not equal to 1. n1 and n2 are not equal to 1 and n is equal to 1. So then ne is equal to 0, n1 comma n2 e is equal to 0. So n1e, if you multiply e inside, then n1e, n2e is equal to 0. So n1e equal to 0 or n2e, either both of the condition will be true. So it is impossible for n is least positive integer such that ne is 0, hence n is a prime. So we have proved both the things. Then we have modular field. So field with non-zero characteristics are known as modular fields. So now we have a note for modular field, that the characteristic of a field is equal to characteristic of a subfield. Whatever will be the characteristic of a field, that subfield will also have the same characteristic. So next topic is field extension. Now next topic is field extensions. Let f be a subfield of k, then field k is called extension of field f. Example, first two examples we have taken. First example, as o comma plus comma dot is a subfield of r comma plus comma dot, so it is extension of o comma plus comma dot r is extension of this. Then similarly, if c comma plus comma dot is an extension, this is an extension of r comma plus comma dot. Now we have the next thing as degree of field extension. What is a degree? So we know that any field forms a vector space over its subfield. Hence k over f, it is written like this, k over f will be vector space if k is field of extension f. Dimensions of vector space k over f is called degree of k over f. So it is denoted by k is to f and with square brackets. So this is the denotation. Then we have examples. So first example is this is equal to 2. The dimension of this is equal to 2. As 1 comma root 3 is the basis of this over the dimension, then 2 is the degree. Now second case is C is to R, which is equal to 2. So C is extension field of R. So C over R is a vector space and its basis will be 1, 1. So dimension is 2. Now we have finite extensions. If a degree of field extension is finite, then it is called finite extension. So if the degree which is finite, then it is called a finite extension, like in case of this example. Otherwise it will be infinite extension. That is, for extension of field K, if K is to F is finite, because we denote it like this, the denotation. If it is finite, then it is finite extension. If it is infinite, then it is infinite extension. Now the last topic. For example, R is to Q is infinite. As R is an extension of Q, so R over Q vector space R is an infinite dimension vector space. Hence we will write this R is to Q is equal to infinite. This is infinite extension. Before we had seen a finite extension. Now this was the example of infinite extension. Thank you.